Okay, so we're going to work on a few basic integrals using the rules that we learned from the concept videos. Um, so the first one is the integral of x to the 7th dx. So what we do to solve that is we need to first raise our base to a power 1 larger than it is. So we get x to the 7 plus 1, which that becomes 8. We then divide by that new number and add c. Done. Um, and that's all there is to it. Second one over here, we have 1 over x to the 8th. So not very different. It looks a little bit different. We first need to change this into one that has a rational exponent. So this is the same thing as the integral of x to the negative 8 dx. And so we do the same step that we did before. We start off, we have x. We raise it by 1. And be careful. Negative 8 goes to negative 7 because we're adding 1 to it. And then we have to divide by that same number. So that's it, plus c. So those basic ones, just keep in mind if you have a negative exponent, adding you just make sure that you're adding correctly. Okay, so another couple that look a little odd to everyone. So the integral of 1 dx. Well, 1 is a constant, right? And so that might mess people up. What does that have to do with x? Well, remember, there's always 1 is always present in everything, and 1 is the same thing as x to the 0. And really, you could say that this is 1 times x to the 0, if that's what you want. But that's the same idea. And so if we were doing x to the 0, we do the same process that we would have had done before. You get 1, which is that coefficient originally, times x to the 0 plus 1, which we know that to be 1, and we divide by this same number 1, which is just, and then we get plus c, this is just x plus c. In the second example, we have x cubed, the integral of x cubed times the square root of x. We have to, in this dx, we have to simplify this first before we move on. This is going to equal the integral of x cubed times x to the 1/2. And we can combine these. Remember, when we combine or when we multiply like bases, we add the exponents. And so 3 plus 1/2 is going to give us 7/2. And so when we go through and integrate this, we're going to end up with x to the 7/2 plus 1. That makes 9/2. We divide by 9/2, and we add c. Now, remember, when we divide by a fraction, it's the same thing as multiplying by the reciprocal of the same fraction. So dividing by 9/2 is the same thing as multiplying by 2/9. And so this would be our final answer. Now some people might like to write it more like this. Makes it make more sense. And you can see that 2/9 times 9/2, that's going to make 1. And you see how we lack any visible coefficient up here. That makes sense. And you'll see this pattern happen quite often. So what happens if we run into something maybe a little more complicated? So like this, where we have the quantity x squared minus 1 times 3x plus 5 dx, and we're trying to integrate this. Well, you might be thinking product rule, but remember, we're integrating. It's a little more complicated. So things kind of have to set themselves up very well to use certain rules. Because both of these are to the first power, like each of these sections, I think foiling it out first would make the most sense. So this is the same thing as the integral of 3x squared plus 5x squared, or excuse me, 3x cubed, plus 5x squared minus 3x minus 5. And this is a really long string of things, but one of the rules that we talked about in the concept videos is that if we're adding or subtracting terms, we can split this up. You can think about it being split up. You don't have to do this every time, but I'm just going to show you that you can think about these as integrating individually. So this is the same thing as integrating 3x cubed dx, and then adding the integral of 5x squared dx, and then subtracting the integral of 3x dx, and then finally subtracting the integral of 5 dx. And then each of these can be dealt with individually fairly easily. So over here, we've got x cubed plus 1, which is going to make x to the 4th. We still have our 3, and we have to divide by 4. Now, we add the plus c, but because we have so many different ones of these, I'm going to label this as C1. Now, this is more of an example of how it works. You'll see what happens in the end, and so hopefully you can kind of avoid having to do this every time. We then add our second part. So we're going to have x cubed, because it's x squared to start. 5 still there. We divide by the new exponent. We're going to add c2 on, because it's the second one. We then subtract away. We're going to have x. It's x to the first, so we add 1 to it. It becomes squared. 3 sticks. We divide by the 2, the new exponent. We add our third c. And then finally, we subtract away. We've got 5x to the 0, so this becomes 5x to the first over 1. And then we add c4 to that. Now, when we put all this stuff together at the end, you're going to have 3/4 x to the 4th. And you're going to have 5/3 x cubed. And you're going to have minus 3/2 x squared. And you're going to have minus 5x. But then we can just throw this big C on the end. And you may say, well, why would we do that? It seems like we have all these other 4 here. Well, those are all just numbers. And so if we're just adding just numbers, then we can combine them all together and just call it some new number. Nothing wrong with this at all. In fact, what you can see is you could skip a lot of this problem. Just integrate each individual part and tack c onto the end. That's all that is necessary, but this would be the long proof of the kind of theorem that I showed you earlier. Then you might run into a situation like this. So I'm going to make this one a little bit simpler than the last. So I'm going to skip some of those steps. But this one you're going to want to rewrite first. And you can use normal algebra to make this easier on yourself. Everything has a base of x, which is fantastic, because what I'm going to want to do is break this up into 3 separate fractions, or 3 separate sets. So I can think of this as the integral of 4x squared over x to the 4th. Minus the cube root of x over x to the 4th. And to save some time, I'm going to call this x to the 1/3. And then finally, you're adding on 6x to the 5th over x to the 4th. And this is all one piece. Well, splitting it up is going to allow me to cancel things out, to simplify it as best I can for each one of these. So right here, 4x squared over x to the 4th, that's the same thing as 4x to the -2. If you move the 4 up, which is, I'm going to do that for each one of these. Move the 4 up, you take it away, it becomes negative 2. Then I subtract away. So if we take away 4 from 1/3, 4 is the same thing as 12/3, so I'm going to get x to the negative 11/3. And we're going to end up with some ugly exponents, but that's okay. And then finally, it should end up here with 6x. All right. So now we're in a place where we can actually go forward and integrate. So do what we've done before. We have x. We raise negative 2 by 1. So it becomes negative 1. Our 4 remains, and we divide by negative 1. Then we subtract away this. We have x. Its original exponent is 1. Or excuse me, its original coefficient is 1. We add 1 to negative 11/3, becomes negative 8/3, and we divide by that negative 8/3. And then finally we have 6x, so we raise x by a power, 6 stays, and we divide by our new exponent, and tack c onto the end. Now we can simplify this. So negative, this term right here, 4x to the negative 1 over negative 1, we can simplify that. So these two terms make negative 4. Our x to the negative 1 is 1 over x. So I'm going to rewrite this as negative 4 over x. Now, this one's going to become a little more complex. Dividing by negative 8/3 is like multiplying by 3/8. Because both of these are negatives, it can be turned into a positive. The x to the negative 8/3, that's the same thing as 1 over the cube root of x to the 8th. So this giant thing becomes positive 3 over 8 cube root of x to the 8th. Really odd looking thing, but sometimes that happens, and you just kind of have to roll with that. And then finally, this last part, this just becomes 3x squared. And obviously we have the plus c. So this is a fully simplified version. It's complicated in that you just have to be very detailed about what you're doing, but knowing how to make it easier on yourself is the key to making these problems much more manageable and quick to do. Now, one of those last things that we looked at was, what happens if we are trying to integrate, a binomial with a power? Well, we learned that you treat it the same way as you would the other ones, but you also have to divide by the derivative of the inside function. So not just dividing by the new exponent, but the derivative of the inside. So this becomes, we're going to have our 8x plus 3. We raise that by 1 power, so it becomes to the 5th. We then divide by that 5, but we have to also consider the derivative of the inside of that function, which is also 8. And so we end up with 8x plus 3 to the 5th over 40. And you can see how we get back to this, right? If we were to take the derivative of this, we have to multiply by 5, right? When we multiply by 5, this down here becomes an 8, right? And we can see that from here. Then we have to multiply by the derivative of the inside, which is 8. And so these go away, and you're just left with 8x plus 3 to the 4th, because then we have to lower an exponent here. So this is one that is, again, kind of the beginning of the reverse chain rule that we have to consider. Last but not least, we have this big ugly problem here. So this is kind of a combination of the last two, in that we have the same base throughout. And we have them mixed into a fraction, real ugly, but what we want to do is we want to split this up and make our life as easy as possible. I'm going to go ahead and switch this to 2x plus 3 to the 1/2. And then subtract 2x plus 3 squared over 2x plus 3 to the 1/2. This whole thing is dx. And so now I'm going to do the same thing that I did with the last problem, or a couple problems ago, where I combine them all together. I'm going to subtract the denominator from the top. So this is the same thing as the integral of 4 times 2x plus 3 to the 3 minus 1/2, which is the same thing as 2 1/2, which is 5/2. We then subtract away. One second. Okay, so same thing for this one. We take our half away from 2, which gives us 1 1/2, which is the same thing as 3/2. So now we can go kind of forward like what we had done before and integrate. So for each part of these, so you're going to have 2x plus 3. We add 4 still out here. We add 1 to the exponent, which is going to make 7/2. We then have to divide by 7/2 times the derivative of the inside, which is 2. Then we subtract away. So we have 2x plus 3. We raise this exponent by 1, which is going to be the 5/2. Divide by that 5/2 and multiply by the derivative of the inside, which is 2. And then tack on c to the end. So this can be simplified fairly quickly. Over here, you end up with 4 times 2x plus 3 to the 7/2 over 7 minus 2x plus 3 to the 5/2 over 5 plus c. And this is as simplified as you can get, right? Basically, the 2's just canceled each other. And this is your final answer. So even as complex as it looks at first, it's still following that pattern. You just need to recognize that most of these problems are just going to have maybe a slick little algebra trick that you can follow to make your life a little easier, but you've got to pay attention to the details. You've got to pay attention to things like, what were the original exponents? What are the new exponents going to be? Any original coefficients? Anything attached to x? You know, what can I do to make my life easier? So take it step by step. Figure out if there's a way to make anything easier that you can. That should be the first step. Can I make it any easier? Then focus on, okay, what parts of this come from a derivative that's already there? And just remember that instead of multiplying everything, we're now dividing. That we're undoing a derivative in a sense. We're doing the antiderivative.